Hi, welcome to my channel, JaberTime. Today we're going to go over the fundamental theorem of line integrals. We're going to talk about conservative vector fields. We're going to talk about independent of path. The fundamental theorem of integrals. The fundamental theorem of calculus, part 2, says the following. In words, it says f prime is the derivative continuous on AB. This whole thing is called the net change theorem. The integral of a rate, that's the derivative of change, is the net change, that's f of b minus f of a. Let C be the smooth curve given by the vector function r of t from a to b. Let f be a differentiable function of 2 or 3 variables whose gradient vector, which is a derivative, is continuous on C. Same language, but using vector calculus, as you could see. Then, the line integral of the derivative, which is called gradient, dr, equals f of r of b minus f of r of a. This is a line integral, and the line integral of delta f is the net change. Again, it's a net change between the end and the start in f. Another way to call it, the line integral of the gradient dr is f of x2 y2 minus f of x1 y1. And this is what we have in 3 variables. Independent of path, that means conservative vector fields. The word conservative will be repeated many times, and you're going to see different aspects for it and different meanings and different comments. So you want to keep in mind what's conservative and maybe gather your notes and make sure that you understand everything about conservative vector fields. One of them is independence of path. In general, the line integral over C1 with the same endpoints should not be the same as the line integral over C2. We saw that in the previous video. The line integrals of conservative vector fields are independent of path. F is continuous vector field with domain D. Then the line integral is independent of path if that is equal to this. That's not happening in general, but that happens where? For conservative vector fields. That's one thing. We're going to keep that in mind. So if you go from A to B along C1 or from A to B along C2, a different path, you'll have the same answer. That's under conservative vector fields. For any two paths, C1 and C2 in D, that have the same initial and terminal points, we have the line integrals the same. Here's a theorem. The line integral is independent of path in D if and only if the line integral equals 0 for every closed path C in D. If you start at this point and you go back to the same start point, for conservative vector fields, we have it 0. It's like the work done moving an object from a point back to the same point will be 0. So this right here in short says the following. C is a closed path f.dr line integral is independent of path if and only if the line integral is 0. Sometimes we just make it a closed path or mention that it's a closed path. Have the same start point and the same end point. Another theorem. Suppose f is a vector field that is continuous on an open connected region. If the line integral is independent of path, then f is conservative. That is, there exists a function f such that the gradient of that f is the vector field itself. Meaning, the line integral of f.dr is independent of path implies f is conservative, which means there is a small f that the derivative of it or the gradient is capital F. Another theorem. If the vector field f is written as p of xyi plus q of xyj is a conservative vector field, where p and q have continuous first-order partial derivatives on the domain D, then throughout D we have dp dy equals dq dx. In short, that's what I have. I'm not writing the details right here, first order partial derivatives, so I just want to give you a quick look. Now, you got to be careful sometimes with those theorems about saying if then or if and only if and so on. This one goes this way. It doesn't go backwards as the converse. Alright? However, sometimes we say P implies Q or A implies B. Let me use A and B instead of P and Q here. A implies B. That's the same thing as negation of B implies negation of A. That is true. Where here, going from A to B, we cannot say that B also goes back to A. So in general, if you have this true, that doesn't mean that your vector field is conservative. There's another theorem that will add to it in just a minute, and I'll show you why. Here's an example. Determine whether or not the vector field given here, x minus yi plus x minus 2j, is conservative. Well, we find dp dy, dq, dx, and they come up to be different. That means f is not conservative. That's like what I mentioned earlier. Negation of b implies negation of a. We're using the same theorem. So that should do it. Now let me support the concept of what is conservative, what's not conservative. Here's a graph of the vector field. This right here. And this is a sample closed curve. The vectors that start on the closed curve, C, all appear to point in roughly the same direction as C. See the vectors right here, the blue ones? It looks like they are pointing as the path on the curve C. C is going this way, counterclockwise. And the vectors, it looks like it's going with it. That means the line integral will end up positive. And therefore is not conservative. It has to be 0 to be conservative, but the graph doesn't show that it's going to end up 0. Of course, one graph is not going to help you all the way, but one by one will help you understand more about conservative vector fields and how do they look in fields and how do they behave with curves like C. Theorem. This is when we say like the converse or going back is not true in general, this theorem adds to it. It says let f be pi plus qj, p of xy I and q of xyj, be a vector field on an open simply connected region. This is called simply connected region. Regions that are not simply connected. Suppose that p and q have continuous first order derivatives, and you have this now. Now you could say f is conservative. So this was not mentioned earlier. If you have that and you have this, you should be able to say f is conservative. What does it mean? It means if you have f, a vector field on an open simply connected region, p and q have continuous first order partial derivatives, and dp dy equals dq dx throughout D, then you say f is conservative. Now, that's not a full credit if you don't mention that. You have three pieces. I know you might say like, oh, I got this, I'm going to say conservative. No. This theorem says you could go back if you have these two are valid. Determine whether or not the vector field given right here is conservative. Well, we have p of xy equals 3 plus 2xy, and we have q of xy equals x squared minus 3y squared. dp dy will be 2x, and dq dx will be 2x. They are equal, and that's a good sign. But we need to add this to the theorem. The domain of f is the entire plane d equals r to the second, which is simply connected. Therefore, f is conservative. So, without saying that, that's not a full credit. You have to be careful, because we said earlier that the theorem does not go backwards. It's not if and only if. To go from B to A, you have to have also this valid. Of course, with the partial derivatives do exist. So, just keep this in mind that this has to be mentioned. Now, to support that the function is conservative, looking at the graph right here, I have two different curves, C1 and C2, and I have clear notes. Take a look. Some of the vectors near the curves C1 and C2 point in approximately the same direction as the curves. Looking at C1, going, let's say, right here, it looks like it's going with it. On C2, it looks like right here it's going with it. Like the black arrow on the curve and the blue ones, the vector field, is pretty much going the same direction. That's right here. Whereas others point in the opposite direction. So I'm underlining the same direction and opposite direction. Take a look at this one right here. Going counterclockwise, you are going this way, where the vectors in blue are going the opposite direction. Same thing here. You're going up and the vectors are going pretty much against you. So it appears plausible that the line integrals around all closed paths are 0. So that's what happens when conservative vector fields, when we say on a closed curve equals 0. So it kind of like balances out. Here's a problem. It says you have capital F, the vector field, equals 3 plus 2xi, 2xyi, plus x squared minus 3y squared j. Find the function f such that the gradient of that f is the vector field capital F. And we're going to evaluate the line integral f dot dr, where c is the curve given by r of t equals e to the t sine t I plus e to the t cosine t j, where t goes from 0 to pi. Now, part A. Well, we did this on the previous example when we added that the domain is a simply open connected region on r to the second. So we're going to take advantage of that. From the last example, we know that f is conservative, and so there exists a function f such that the gradient of that f equals the vector field f. Meaning, well, if that's true, this is the gradient. That's the gradient. Equals capital F equals capital F. That means this is the partial derivative with respect to x, and this is the partial derivative with respect to y. Let's put them on the side and keep it in mind. Now, step by step, you don't have to start the same exact way, but the concept is the same. You could start with fy. I started with fx. You don't have to. You could double check, and it's a good practice. But follow me piece by piece. Here we go. We are saying or claiming that this is the partial derivative with respect to x. Right there. We're going to integrate this with respect to x. We're going to take it back. 3 becomes 3x. 2xy becomes 2x to the second over 2. 2 cancels y. Plus the constant of integration. But this time we're not going to write c like single variable calculus. We're not. We're going to write g of y. It's a function of y. Could have y. Doesn't have to have y. But imagine if this is y plus 7. And when you take it back this way, you're going to differentiate with respect to x. So the y and the 7 will cancel. You don't see it here. So in my point of view, x is my variable. So my constants could have a y in it. Just be careful with that. Now, one more time, it's like a game. This is my first step. Started with fx, I took it back. Integration with respect to x. Now I'm going to differentiate this with respect to y. So I started here, I'm going to go around and come back to this. Differentiate with respect to y and compare it to this right here. 3x will be 0. X to the second y will be x to the second. G of y will be g prime of y. Compare this to this. I'm using the same color to tell you where I'm looking back and forth. X squared, I have it, minus 3y squared, that should replace this. That means g prime of y equals minus 3y to the second. Okay, now we have g prime with respect to y. We're gonna integrate this with respect to y to take it back. Integrate with respect to y. And I have minus 3y to the third over 3, which is minus y to the third, plus some constant. This time we're not going to write x because we don't have any x's involved. And we're going to go to the constant. Instead of writing c, we wrote k. Now, so if the g of y equals this much, I could take it and put it right there. Now I know what's f of xy. And that should do it. I'm using the same color to tell you where I'm getting this to which part. Put this right here instead of that, and I have the following, and that is my final answer for part A. If you want to double check, you could do that. Take this and find the derivative with respect to x. You see this is a constant. Will cancel these two. This will give you with respect to, what did I say, with respect to x? That will give you what? 2xy. It's right there. That will give you 3. It's right there. Let's do it with respect to y. 0. I don't have anything for it. With respect to y, I have x to the second. With respect to y, I have negative 3y to the second. And k will be 0. That should do it. Next. Next. Part B. Evaluate the line integral of f.dr along the curve C, where C is the curve given by r of t equals e to the t sine t plus e to the t cosine t, and t goes from 0 to pi. This is the line integral. We're going to replace f with the gradient. We're going to do the fundamental value theorem for vector calculus, line integrals. So all what I need to do is find the endpoints as vectors and we'll plug them in. Here we go. we have r of t given to me. And when you have a 0, plug it in here, I get this, which is 0, 1. So that's my start point. When you have pi, plug it in here, take your time, and that's my end point. The problem right here, or the function f that we found in part A, the constant of integration for definite integrals, we don't need it. As you know from single variable calculus, when we integrate with limits, we don't write c. Even if you write c, it's going to cancel. So we're going to do the same here. Any value of the constant k will do. So let's k equals 0. The line integral is the same as the line integral of the gradient dr, and this is the fundamental value theorem for line integrals. That's f of the endpoint minus f of the small point as a net change. Just plug in 0 for x, plug in minus e to the pi for y, and that should give you e to the 3 pi. Let's double check. 0 for x, 0, 0. These two will cancel. We said that we don't need to worry about k. Minus e to the 3. Plug in negative e to the pi. Negative e to the pi to the power 3. The negative stays. We have another negative that makes it positive. Just to let you know that this is all what I'm doing. Plugging in the numbers right here for x and y. And that should do it. Thank you for watching, and I'll see you on the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.